Okay, we're ready for question number 5 in our packet, and this one is about a situation with a geologist. So chemistry is all over the place, from pharmaceuticals, which we saw in the last video, to fuels, to plastics. In this case, a geologist looking at a mineral sample. There's chemistry in a lot of things. So just for something different, in this question, we're looking at a geologist. So on the field, I'm finding rock samples, I'm studying what's in them, and I want to identify the particular minerals that make up the rock. And so in this story, the geologist is analyzing a sample that was taken from a rock core and has found that this mineral contains potassium, aluminum, silicon, and oxygen. Now, these are 4 very common elements in many minerals. And the story in this problem goes that there are at least 3 choices that the geologist can choose from, and these 3 choices are listed here in the table. They all have potassium, aluminum, silicon, and oxygen, all 4 of them, just in different proportions. And you can see in these various formulas that there's 3 different combinations of the elements. Potassium, there's 1. Aluminum, there's 1. Silicon, there's 3 or 1 or 2 atoms in a molecule. And oxygen, there are 8 or 4 or 6. So the empirical formulas and the molecular formulas of these compounds are shown here, and they're all a little different, but they all made up the same elements. So to figure out which one it is, we need to do a little bit of analysis. And the math that we're about to do here is kind of like the stuff we did in questions 1, 2, and 3, at least for the first part of this problem. And then we go on to a couple of conversions that are a little bit more like what we saw toward the end of number 4 as parts B and C here. So for part A, let's start out with looking at the data that's given for the 4 elements here, and do an empirical formula, a molecular formula. In this case, they're sort of interchangeable because they can't be simplified. None of these 3 can be simplified. So as we look at this one, let's see what we can figure out as far as its molecular formula. So we have, in this case, 14.1% potassium. I remember from an earlier video that percent means out of every 100. And in this case, if we had a 100-gram sample of this mineral, 14.1 grams out of that 100 would be potassium. So the way we handle these problems is to say that in a 100-gram sample, there would be 14.1 grams of potassium. And again, we're not studying a sample that large necessarily. We might be studying one far smaller. We might be studying one much larger, in fact. But the idea is that out of any 100 grams of this mineral, there would be 14.1 grams of potassium. 9.7% is aluminum, so I'm going to put that down, 9.7 grams out of 100. Silicon, 30.3%, which means 30.3 grams of silicon. And then the oxygen is the remainder part. And we've seen that before. We have to do some subtraction to figure out what's left over. So I'm going to grab my calculator here real quick and subtract that out. 100 minus my potassium, which is 14.1, minus my aluminum, which is 9.7, minus my silicon, which is 30.3. And we find the oxygen is almost half is oxygen. So that's 45.9%, or grams out of 100, would be oxygen. Oxygen is the most abundant of the elements in our Earth's crust, in the crust layer of the Earth. There's a lot of silicates, and silicates are a very common mineral. It's in many different kinds of rock. Granites are silicates, all kinds of them. In the crust of the Earth, there's a ton of silicon and oxygen. Oxygen is first most common, and silicon is second most common. In fact, you can see that right here in these formulas, that oxygen is the most dominant element in all 3 of these, followed by silicon, and then aluminum is right behind. I think aluminum is the 3rd most abundant element in the Earth's crust. It's right up there, and potassium is quite high too. But that's geology, and I have a master's in geoscience, so that's a little interesting to me as well, but it doesn't matter as much here. So we need to get all these converted. 1 mole of potassium, we haven't used that one before, so that's fun. 1 mole of aluminum, we haven't used that one before in any of the problems we've done. Oxygen, we've seen that one, so that one we're familiar with, hopefully. If not, go to your periodic table. Don't feel like you need to memorize it. It just makes it faster. Right? So for the rest of these, we need their masses. How many grams of silicon? How many grams of aluminum? How many grams of potassium? Now, I've used these for years. I know these numbers pretty much by heart, but we'll go look at them on the periodic table, so you make sure and look them up too. And you can see here that silicon is 28.09 grams. That's here. Aluminum's right next to it, 26.98 grams, and the other one was potassium at 39.1. Okay. So those are the 3 we need. Silicon, 28.09. aluminum 26.98, and potassium 39.1. Okay, so I need to just do my math here, get these all converted into moles, and so I'll punch those into my calculator real quick here. Potassium 14.1 divided by 39.1. There's my potassium moles. 9.7 divided by 26.98. There's my aluminum moles. And write those two down real quick. 0.36, we'll go 0.361 moles of potassium. For aluminum, 0.360 moles of aluminum. Well, look, before we go any further, that makes good sense, right? They're basically the same. That's going to be a 1-to-1 ratio of them, of those two elements. And what do you know? All three of our choices up here have a 1-to-1 ratio of potassium and aluminum. So that's pretty obvious that that makes sense. That doesn't rule out anybody just yet. Okay? So let's see what the next one is. Maybe that's going to shed some light on things. 30.3 divided by 28.09 gives me 1.08. 1.08 moles of silicon. And oxygen, we said oxygen was the most abundant of the elements in the Earth's crust. So it should be the largest number of moles here, and it is 2.87 moles of oxygen. Now, we can look at this and kind of do what we've done before to kind of confirm it for us a little bit as well. But I'm starting to notice here that silicon is 3 times larger than aluminum, and silicon is about 3 times larger than potassium. Now, I'm gonna show you how we can confirm that real quick too. The smallest one of these 4 needs to go on the bottom, as we've done with the other problems, and when we divide to find our mole ratios, right? So aluminum's slightly the smallest. Put that aluminum down here, and we're going to have 0.360 moles of aluminum. We're going to have 0.360 moles of aluminum here, and we're going to have 0.360 moles of aluminum here. Now, we already saw this one's more or less a 1-to-1 ratio, 1 potassium for 1 aluminum, right? If we do the division on this one, we're going to find this is a 3-to-1 ratio, 3 silicons for every 1 aluminum. And you might look at your choices and recognize that right away that's pointing us toward this first option, which has 3 silicons for every 1 aluminum. And if we finish that out, we're going to find out down here that this ratio comes out at 8-to-1. So 8 oxygens for every 1 aluminum. And in fact, the formula that would give us then is K1, Al1, Si, 3O8, and sure enough, that's sanidine. Okay, it's not a mineral I'm real familiar with, but that's the one we're looking at right up here in our list. So it is sanidine. So therefore, our answer is sanidine. And again, one of several elements, or rather minerals in this case, that all are made up of the same elements, just in different proportions. So this is why empirical formulas matter, why molecular formulas matter for geologists, because they can help them to identify what kind of rock it is. And if I was doing a study of plate tectonics, I might look for this particular mineral of a certain age on various continents and be able to make some kind of conclusion that perhaps those continents had fit together earlier in time, and now we've had drift and the continents are apart. So even if you're not thinking about chemistry as your future, maybe you are interested in geology, and there's certainly a lot of chemistry in geology. So we figured out in this example that sanidine is our mineral in question. Now that we've done that, we can go on to questions B and C, and frankly they're quite a bit simpler than all this for empirical formula. The question for part B says how many moles of silicon would be found in a 27.9 milligram sample of this mineral, of the sanidine we just discovered. So we have a 27.9 milligram sample of sanidine, and I'm just going to call that SAN for short. Okay? They want to know how many moles of silicon would be in there. Well, remember that our general guideline is when in doubt convert to moles, because that's probably something you're going to have to do anyway. So let's get these milligrams of sanidine into moles of sanidine. All right, 1 gram of sanidine will be 1,000 milligrams. And that's a conversion we can do real quick here. That's 1 gram equals 1,000 milligrams for anything, right? In this case, milligrams will cancel out and we'd have grams. I'm going to go ahead and string another step on the end of that, though, because I'm not quite done with that yet. I don't have to stop and get an answer here because that's not where I want to be when I'm done. I want to go a step further and be able to say that 1 mole of sanidine has how many grams? Again, when in doubt, convert to moles, and we haven't done that until, well, we're about to, right? So 1 mole of sanidine would mean I have to go to the periodic table and I have to add up, okay, all the atoms in that molecule up here. Now it's getting a little cluttery. I don't like to have a big mess here, so let's clean that up. We're mostly interested in this first formula, so let's look at that one. And so we need to add this up. How many grams would be in 1 mole of that? So I'm going to go back to my periodic table, or my atomic masses, and add this up. I need 1 potassium, that's 39.1. I need 1 aluminum, that's 26.98. I need 3 silicons, we decided, because it is that formula, and silicon is 28.09. Oops. And I need, let's see, 8 oxygens, so 8 times 16. So for a grand total of 278.35. So that's going to go down here. 278.35 grams is equal to 1 mole. When we add that up, we can say this is an equality statement. 1 mole is equal to 278.35 grams. We can say that 1 gram of sanidine is equal to 1,000 milligrams. And remember, we can put whatever we want top and bottom in these boxes as long as they're equal signs or equalities, or there are some sort of appropriate ratio. And so here, 1 mole is 39 grams. 1 mole is 26.98 grams. And we've done that with every mole conversion that we've really been doing along the way, and all those empirical formula problems too. Now, when we set it up as a ratio in our ratios here, we're not really saying equals or equal to. We're more saying per. So 1.08 moles of silicon per every 0.360 moles of aluminum is more or less the idea. So more on that as we go. Grams of sanidine will cancel out, and this would tell me moles of sanidine if I stopped right now. Okay, but that's not what the question's asking me to find out, moles of sanidine. It wants to know how many moles of silicon is there in that sample. And we've taken that 27.9 milligram sample we started with here, and we've done a couple things to it mathematically. We haven't punched it into the calculator to actually get an answer yet, but we could stop right now, punch it in, have an answer, and that would be moles, and that'd be fine, but it wouldn't be quite the end. So let's not stop till we're at the end. If we're looking for moles of silicon, we need to have some way of relating moles of sanidine, this molecule, to moles of silicon. How are we going to do that? What I can do is I can look at this formula that we figured out. I can say that for every 1 mole of sanidine, there are 3 parts silicon in there. We can say 3 moles. 3 moles of silicon. For every, let's take the lines off this for just a moment, just to kind of make it a little bit easier to do what I want to do here. For every 1 of these big things, it's got all these different parts in there. It's got 1 potassium, 1 aluminum, 3 silicons, and 8 oxygens all put together. And so there are 3 silicons for every 1 big sanidine molecule, okay, unit here. And so when I write it here in my box, down here in my conversion, I'm not saying that 3 moles of silicon is equal to 1 mole of sanidine. We're not saying it's equal, but we are saying per. So it's a way of saying 3 moles per 1 mole. 3 moles of silicon per 1 mole of sanidine. Okay, that's like saying, I don't know, 3 slices of turkey for every 1 sandwich. It's kind of a 3-to-1 ratio. And we're having that here in our formula as well. So now we're ready to go ahead and punch this into our calculator and get a final answer, because moles, if I punch it all in, the unit that's left over is right here at the end of my boxes. It's at the top. Every other unit has canceled out, and my calculator is going to say some number of moles of silicon, and that's what the question wanted me to do. All right, so the time has finally come. 27.9 divided by 1,000. I also need to divide that by 278.35, and then I need to take that whole thing times 3. Okay, and so the answer comes out here to be 3.01 times 10 to the negative 4th moles of silicon. So not very much. Right? Not a lot of silicon. Does that seem realistic? And that's a good thing to ask yourself. Well, we only started out with 27.9 milligrams of sanidine. That's just a tiny, tiny little little crystal, little piece. So in that, there's not going to be a lot of silicon because it's a tiny little sample. We're talking about a very small amount of silicon and a very small sample of this mineral. So it makes sense. Okay. Now, if you're not quite looking at my math here and say, how did you get 27.9 divided by 1,000 divided by 278? How did you do that? I just like to work this left to right. So it's really 207 or 27.9 times 1. I don't need to show that. Divided by 1,000 times 1. I don't need to show that. Divided by 278.35 times 3 divided by 1. I don't need to show that. You can just leave all the ones out because multiplying and dividing by ones does nothing, right? So if I just take the other numbers into account, when it's on the bottom, I divide by it, and when it's on the top, I multiply by it. And if you're not quite comfortable with that, feel free to just multiply all the top numbers together and write it down, and then multiply all the bottom numbers together and write it down, and then punch those into your calculator, dividing top by bottom, and you'll get the same answer that I do every time, okay? So feel free to see me with questions on that if you're not quite comfortable with how I did the math at the end. Now, one more question to go. It says how many moles of oxygen would be found in the same sample? That saves us from having to do a lot of work in the same sample. So for question at the end here, my final calculation on part C, and then we'll be all done with this, baby. I'm going to just give myself a little bit more space. For my final calculation, I'm going to do a one-stepper, really quick, okay? I can start all over and do all this math again and end with oxygen instead, or I can simply say that because I've already gotten to silicon at the end of my last question, I've got 3.01 times 10 to the negative 4 moles of silicon from my previous answer. I can go back to my formula here, and I can say that in my formula, there are 3 silicons for every 8 oxygens. Or another way of saying that, there are 8 oxygens for every 3 silicons. It's a 3 to 8 ratio. 3 moles for every 8. Remember when we did our empirical formula before, we found at the end that there were 3 moles of silicon for every 1 mole of aluminum, and there were 8 moles of oxygen for every 1 mole of aluminum. And because those are linked to each other through the aluminums, we can simply say that there are 3 moles of silicon for every 8 moles of oxygen. And that's it, right? So what does that mean to me here? That means I'm one step from answering this question. I can simply say that there are 8 moles of oxygen for every 3 moles of silicon in this compound. Now, be careful here. Don't get so hasty, oh, this is super simple, and flip it upside down. You still need to put it in here in such a way that my units will cancel out and leave me with moles of oxygen, right? This would be just as true if I wrote it upside down, but moles of silicon wouldn't cancel unless they're in the denominator here, and oxygen needs to be on the top because that's the answer that we're kind of heading to in the end anyway, all right? So, punch this into my calculator. I've already got it stored, right? It's my previous answer. So, in most calculators, and probably yours too, if I just hit times 8 divided by 3, I'm going to say that answer, right? Times 8 divided by 3. And it says the answer should come out to be 8.02 times 10 to the negative 4. Oops, what the heck? Times 10 to the negative 4 moles of oxygen. Okay. Boom. Without having to do a whole lot of extra math, we were able to take one thing that we'd figured out and relate it to the next thing. One more step. And hey, just take a quick look at these quantities. There's about 3 times 10 to the negative 4 moles of silicon, and there's about 8 times 10 to the negative 4 moles of oxygen. Right there is our 3 to 8 ratio. It's right there in the answers, right? So it kind of reinforces for us the structure and the formula that we found before. Okay, that's question number 5. One more to go in this packet, and if you're still following along and going through these with me, I appreciate your commitment. It will pay off for you. Question number 6, one more to go. I'll see you then.